Greetings, mathophiles, and welcome to a discussion of some issues around the probabilities involved in rapid antigen testing for COVID. We need to start by making very clear that this is not medical advice. This is for educational purposes having to do with the study of probability. If you have any questions about your own health, any questions about what tests you should be taking, or how to interpret any tests that you may have taken, that's for your physician. That is not for me or anything on YouTube. So there exists a rapid antigen test called the Binax now, produced by Abbott Laboratories. I happen to have chosen this one because I've taken it a couple of times. And I want to investigate some issues having to do with how likely one is to be uninfected if one tests negative, how likely one is to be infected if one tests positive. Tests are not perfect, of course. Sometimes there are false positives. A person who is not infected shows as infected upon taking the test. Sometimes there are false negative. A person who is infected shows as being uninfected. They come up with a negative test. And in the world of testing, these things are measured with two scales, if you will. One, the sensitivity, and another, the specificity. The sensitivity of a test is the probability you test positive if you have the condition. The specificity of the test is the probability that you test negative if you do not have the condition. And of course, ideally, these numbers are as high as possible. In asymptomatic individuals, and you may have seen this in the media, in asymptomatic individuals, the test is not quite as sensitive or as specific as it is in symptomatic individuals. And so we're going to start by looking at asymptomatic people taking this Binax test. And in a future video, we will take a look at what happens for the symptomatic and what those numbers are and how that all plays out. These numbers are from a CDC article, and I'll flash the information on the screen. I'll also place it in the video description so that you can peruse it at your leisure. This is based on observations in Pima County, Arizona for a couple of weeks in November of 2020. So here's the deal. The sensitivity of this particular test is 0.358, meaning the conditional probability that you test positive given that you have an infection is 0.358, which is rather low, right? And the specificity, the probability that you test negative, is 0.786, which is also maybe not as high as we would like it to be. So we might ask ourselves, what's the point in even using these tests? And it turns out there's value, as we'll see. So we're going to make use of the fact that there's really a 2-by-2 situation here going on. A person will either test positive or test negative, and a person will be either infected or not infected. And of course, of these four cells in the center of our contingency table here, the upper left and the lower right are the ones we'd like to be. We would like infected people to test positive. We would like uninfected people to test negative. Now, what we're going to need to know or assume as part of this investigation is what the likelihood is that a person is infected in the first place. So if I grab somebody out of the population, what's the probability that they are generally infected with COVID? This is going to vary from over time. As you know, there have been surges and lulls. This is going to vary geographically. At different times, case rates are higher in some places than others, and these things move around. So we're just going to make a flat out assumption that about 5% of the people in some population have a COVID infection. I suspect this is high for most places most of the time, but as I record this in early April of 2022, there was a recent article, and I'll post a link in the description as well. There was a recent article suggesting that 1 in 13 people in the UK at the moment is infected with COVID, which would be 7 and a fraction percent. So in a surge, perhaps the 5% number is reasonable. It's certainly speculative, but it gives us a basis for beginning our discussion. So certainly then 95% of the population under this assumption, and it's only an assumption, 95% of the population would be uninfected. And of course, those would have to add up to 1. So now what? Well, if the probability of an infected person testing positive, i.e. the sensitivity, is 0.358, then if I multiply 0.358 by 0.05, that should give me the fraction of the population in decimal terms that is both infected and would test positive. And that is, if I do the arithmetic, which I've done ahead of time for convenience, 0.0179. Then we need to look at the specificity. So 78.6% of the 95% of the people who are uninfected would test negative. And if I take 0.786 times 0.95, I get 0.7467. And now I have all the information that I need to fill in the rest of this contingency table. So 0.05 minus 0.0179 happens to be 0.0321, and 0.95 minus 0.7467 happens to be 0.2033. And if I add these up, I get 0.2212. And if I add these up, I get 0.7788. And as a little check, I can add these two values and they should sum to 1, and indeed they do. Now, questions that are of great interest to us include, what is the probability that somebody is actually infected given that they've tested positive? I grab an asymptomatic person out of a population, I give them a test, the test shows positive. What's the probability that they're actually infected? That is going to be the probability that they're infected and positive, 0.0179, divided by the probability that they are positive, which is 0.2212. And this works out to be about 0.08. In the asymptomatic, this test may not be of all that much value in identifying who has an infection, given that the probability that you're infected with a positive test is still rather low. However, another thing of interest would be this. What's the probability that you're not infected, given that you've tested negative if you're the random subject? Well, the denominator is going to be all the people who have tested negative, which is 0.7788. The numerator is going to be all of the people who've tested negative who are uninfected, that is 0.7467, and that turns out to be about 0.96. And so it would seem that the value in an antigen test among the asymptomatic would be for identifying people who don't have it. If you are drawn randomly from a population with a 5% rate of infection and you test negative, the probability that you are uninfected given that condition is 0.96. And that would seem to be a very helpful thing to know. Of course, it's possible that we might change our minds or gather new information or simply want to test some other assumption about the fraction of the population that may be infected with COVID. And we would hate to have to redo that contingency table every single time we wanted to imagine a new number or we were faced with new data. And so what we're going to try to do now is to construct generically for any fraction of people infected in a population the contingency table and then the conditional probabilities that we looked at a moment ago. So if P as a decimal of the population is infected, then of course 1 minus P is not, and these will total 1. If the sensitivity of the test is 0.358, then the fraction of the population that will both be infected and test positive is 0.358p. 35.8% of the positive folks will test positive, or the infected folks will test positive. Down here, we've got the specificity of 0.786 times the fraction 1 minus p who are not infected. And in a fashion similar to what we did with the assumption of a p equals 0.05, we'll just do the arithmetic and fill these all in so that the rows and columns add up the way they need to add up. So this is 0.642p. This is 0.214 times 1 minus p. If I collect some like terms, this is 0.214 plus 0.144p. And this is 0.786 minus 0.144p. And to our relief, those add up to 1. Now, what's the probability that someone is infected given that they tested positive? Well, the denominator is going to be the fraction of people who have tested positive, which is, or the probability that somebody tests positive, which is 0.214 plus 0.144p. And the numerator is going to be all the folks who both were infected and tested positive, which is 0.358p. And you can check this by plugging in a 0.05 and seeing if we got the same value that we got a couple of moments ago. Over here, our denominator is everybody who tested negative, which is 0.786 minus 0.144p. Our numerator is everybody who tested negative and was not infected, which is 0.786 times 1 minus p. This now gives us an ability to graph these functions, the conditional probabilities, as functions of p. And then we can ask ourselves very easily, if this is a fraction of the population that's infected, what is the probability that someone is infected if they tested positive versus not infected if they tested negative? And so we're going to switch over to Desmos in order to examine that. Here is a graph of that first function, the probability of somebody being infected given that they tested positive as a function of the presumed probability that someone at random in the population is actually infected. I'm going to add a little slider with a little label here, and we'll move this thing around a little bit. So you'll recall our first assumption was that 5% of the population was infected. And as you may recall, we saw that under that circumstance, the probability that somebody is infected, given that they tested positive, is only about 8%. And as this rises, as the p's rise, of course, those conditional probabilities rise. But even in a situation where you got a ton of COVID floating around, 16% of the population with COVID, your probability of having it, given that you've tested positive with this antigen test, is still only about 24%. And of course, most of the time, most locations are over here near the origin. Typically, the fraction of the population of people who are infected is not incredibly high. Here is the other conditional probability, the probability that you are not infected, given that you tested negative, as a function of the probability, unconditional probability that somebody in the population would have COVID. And you may recall from near the beginning of the video that under the assumption that it was 5% in the population, the probability that you are not infected, given that you tested negative, is about 96%. And so this would seem to me, as a layperson, to be the real value of the test. That as we spend our time over here near the 0.01, it is the case that our probability of being uninfected, given that we test negative, is pretty high for any reasonable assumption about the fraction of the population that is infected. There are a number of cautions and caveats and disclaimers that we should discuss. The first being a reiteration of what I said at the beginning, which is that I am not a medical professional, and this is not medical advice. This is just a math guy messing around with the numbers as they've been published. Second, the value of this to you as an individual in interpreting a test that you may have administered to yourself is awfully limited. We chose to imagine that somebody was selected at random from a population where there was a given likelihood of having a COVID infection. But everybody's likelihood is more individual than that. Some people are vaccinated, some are not. Some mask rigorously, some do not. Some people spend more time out in the world around other people than do others. If you live alone, if you work remotely, you don't go out much, you take precautions when you do, your sort of individual likelihood of having COVID might be quite lower than that in the general population. If you have just been to an indoor show and you were unmasked and everybody around you was unmasked and having a great time, your particular likelihood on a given day might be quite a bit higher than the likelihood in the population. And of course, at the end of the day, this isn't really a matter of probability for a given person at a given time. You've either got it or you haven't on a given Thursday. And so there's a limit to the usefulness of this discussion tremendous limit to the usefulness of this discussion for understanding what your situation may be given that you had a given outcome on this test. But it is interesting to work these numbers out and to see that the usefulness of this test maybe is not so much in identifying the sick as in identifying the not sick, which in itself is a valuable thing. So don't make any medical decisions based on anything I've said. But I do hope that you have enjoyed this discussion, and you have found it useful in learning a little bit more about probability. Happy mathing.